So we're going to talk about the wave-particle duality here. What is the wave-particle duality? We're going to use light as an example, and the question is light a wave or a particle? Historically, it was thought of as a particle back in by Newton, and later on Young performed some experiment that demonstrated that light is a wave. The true answer is that light is both a wave and a particle, depending on how you look at it. Schrödinger said that all matter has a wave function, and as Feynman explained it, waves behave like particles and particles behave like waves. Everything behaves the same way, so there's no distinction between waves and particles. So just kind of give you an idea of what that means, it's kind of like two different visions of a single object. A simple example to demonstrate this is a cylinder. So here, if you look at a cylinder from the side view, you'll see an outline of a rectangle. If you look at it from the top view, it is a circle. Now, is it a circle or is it a rectangle? Well, it's both, depending on what way you look at it. It's not a true representation of what the wave-particle duality is, but it's kind of a start of what it's all about. This is another representation that I like of the wave-particle duality. It's water. Is it a wave or a particle in here? And as you can see from this drop, it's a particle, and as you see here, it's also a wave. So that's kind of an idea of what this is all about. It's both, depending on how you look at it. And this all came from the double slit experiment. To kind of give you an idea about that, let's talk about single slit. So here, if you send particles out and you send it through a barrier that has a single slit, what you would expect is on the screen behind it for the particles to form on the screen the same way as the slit is here. So it's kind of like sending bullets or marbles or whatever the case through this barrier that has a single slit and seeing what comes out on the other side, and that's what you get. Now waves are a little different. You send a wave through that same slit and you have diffraction, and as you can see right here, wave comes out, and if you're going to have a screen right here, what you'll have is the point of contact at one point. So they kind of look the same between waves and particles. So if you take it to a double slit, if you send particles or matter through a barrier that has a double slit, what you'd expect to see is, two slits on the screen right here. I mean, just intuitively speaking, this is what you expect. Things go through one slit, and so waves are a little different, however. So if you send waves through a barrier that has two slits, you'll get an interference pattern like this. This is kind of like my picture of waves. It's not very good, so I showed a picture here. What's going on here is waves are being formed with these two balls in the lake, and the wave pattern from these two balls is like this. So these right here are interference patterns. This is where you have constructive interference, where the waves combine to make a higher amplitude, and right here, these dead spots, so to speak, are destructive interference. So if we were to put a screen right here, you would see that it would come out. You'd see a mark right here, a mark right here, and a mark right here, and so on and so forth. So they did this experiment with electrons. What are electrons? They are part of an atom, so we would naturally think that these are, particles. So they sent them through a double slit experiment, and what they found is that it showed the interference pattern of a wave. So they were like, well, what's going on here? These are electrons, they're charged, maybe they're interfering with each other. So they adjusted the experiment. They would shoot out one electron at a time, came back an hour later, and they had the same result. They had an interference pattern on the screen. And, they're like, well, what's going on? That doesn't make sense. There's one electron coming out. So is it going through one or the other, or both, or none at all? It just didn't mathematically make any sense. So what it was doing is that it was going out as a wave and then coming back to hit the screen as a particle. So they wanted to, they wanted to know what was going on. It was behaving very weird, something that we weren't really used to. An electron coming out, becoming a wave, and going through both slits interfering with itself and hitting hitting the wall like it was a particle. You can kind of think of this as, sound, where someone's talking and the waves go out, but only one person hears it. So um, again, that's not a perfect representation of it, but it's kind of an idea of a way to think about it. So you're coming out as a wave, only one person is perceiving it, so it's hitting one person at a particular point. So they were really curious as to what was going on, so they decided to observe it. So they put in a device to see where the electron was doing and what was going. And what had happened was really strange. It started acting like a particle again. And this was the result right here, is that it would hit the screen and the pattern would act like a particle. So really measuring what was going on was showing that it behaved like a particle and it no longer behaved the way it used to. So it was kind of like nature's little trick is, like, I'm not going to let you find out. But really what it is the wave particle duality. It could be either way depending on what you look at it. So all particles really do exhibit both particle and wave properties. So it all depends how you look at it, and this is, this experiment and the wave particle duality is what led to the uncertainty principle, which we will talk about in a minute here. But that, in a nutshell, is the wave particle duality.